Hey guys, my name is Ali Alqaraghuli. I'm a systems engineer and a postdoctoral fellow at the NASA Jet Propulsion Lab. In this video, I'm going to show you a comparison between electrical engineering and computer engineering from a curriculum perspective. What I mean by that is by the end of this video, you will have gone through every class for electrical engineering and for computer engineering, seen what the similarities are, what the differences are, and hopefully that will help you decide whether you are studying the right major or whether either of them is for you. So what I have over here is two flow sheets. Shout out to the university where I graduated my bachelor's and master's from University of Buffalo for making those. Those are super, super cool sheets that basically show you the progression of the classes and the curriculums. So what I'm going to go ahead and do is I'm going to show you year by year what the classes look like. On the left side, I have the electrical engineering curriculum. And then on the right side, I have the computer engineering curriculum. Another reason I'm excited to make this video is because although I did my bachelor's, master's, and PhD in electrical engineering, I currently work as a systems engineer mostly, meaning I have to know how to do hardware as well as software, as well as physics. I have to know everything. And when I was going through college at the time, I was studying electrical engineering, but my best friend was studying computer engineering, and we would always share with each other what we were learning. So it's pretty cool. I kind of got to experience computer engineering through his lens, and he got to experience electrical engineering through my lens over here. So in the very first year, you take calculus in both majors. Now, calculus is a very, very important math class. I'm not going to go too much in detail about the classes from the first year, the math and physics. Basically, in calculus, you learn about rates of change. You learn about how things are changing, whether they're changing fast, whether they're changing slow. That is absolutely crucial to like how everything functions in the real world, especially in engineering. Now, as you can see, something really cool about these flow sheets is when you highlight a class, it shows you like all the other classes that are built on top of this. So for example, if you don't pay attention and you don't like get really good at calculus and you don't have a deep understanding of what a derivative even is, you're going to like struggle in a lot of these other classes because everything kind of is built on top of that. Everything, all these other classes, because they're studying phenomena and they're building phenomena that are constantly changing in the real world. If you don't even understand the math of change, which is basically Calc 1, then you're going to really, really struggle. On the contrary, for example, a course like Chemistry 1, it's not really going to impact anything that you do. Maybe if you go into like, I don't know, batteries or like, I don't know, like atomic physics or something like that, then you obviously need to get a very, very good understanding of atomic particles and just kind of a very basic understanding of inorganic chemistry in this case. But in this case, if you don't really pay much attention in chemistry, no one really cares as much. You just got to survive this class and get through it. You take the same in computer engineering. So far, they're the exact same. The only difference is that here you take EAS 199. In computer engineering, you take an introduction to computer science. Now, basically, this class right here is an engineering introductory course on building a project of some sort, like whether a wind turbine or something like that, which involves mechanical aspects, electrical aspects, and a little bit of software aspects. The goal of this class is really just to kind of get you exposed to what engineering even is and get you very quickly to learn like whether engineering is for you or not. On the other hand, in computer engineering, you take intro to computer science. In this case, this is CSE 115. Obviously, in each university, the numbers and the names are going to be different. But this class, Intro to Computer Science for majors, even though it's supposed to be an introductory class, I mean, in theory, you learn the very fundamental basic stuff. Like in this class, you learn things like, oh, that looks way too large. In this class, you learn things like variables and functions, and basically how to write your first few lines of code. But then the class becomes very, very difficult way too quickly. Also, depending on which programming language it is that is used to teach this course. Generally speaking, it's Java because it's an intro level course, and you want to use an easier language such as Python or Java. If your school is hardcore, then they may use something like C++ or C, which I think would be an absolute nightmare and an awful decision to teach to like a very first freshman fall semester, because you're going to burn them out with like very tough programming language, very tough syntax. I think a really good school, a really good program that is well designed will have this course built either in Java or in Python, in my opinion, or something of that nature. Now, again, while in the fall semester, you're learning the very basics of software, just kind of, again, functions, variables, things of that nature. You build your first project, you build your second project, you may build a calculator or something like that. In the follow-up course in the spring, there's Intro to CS Major 2. Generally speaking, here you start learning, you start diving deeper into object-oriented programming. So you start, instead of just like having like a very simple sheet with a bunch of lines of code on it, you start having building kind of like writing code in a more systematic way and working on more advanced projects. These two classes in the first year really, again, just kind of introduce you to software. They teach you the kind of foundations of it. They don't dive like too deep into either the math nor the coding. It's just kind of, again, touching the surface. And these are generally weed out classes. These are classes to see, are you someone who's willing to sit down and do the work and actually learn how to program and learn how to be really good? Or are you someone who just like watched a couple of videos on TikTok and thought like getting a tech job is cool and high paying and you can do it remote, and you like were not prepared to do any work at all? So really, really good classes over here. You take Physics 1 also, which is mechanics. Again, basically the physics of motion. I have other videos talking about it. I'm not going to touch about this too much. Then you take Calculus 2, which is the follow-up to Calculus 1. It's, again, it's the mathematics of, generally speaking, integration. Basically, calculating, taking very, very small things, putting them together and observing like macro behavior as a summation of like micro behavior. It's a very, very cool concept, integration in general. It's not the only thing you learn in Calc 2, but it's kind of the core fundamental concept in Calc 2, where Calc 1 is more about derivatives and rates of change. Calc 2 is more about integration and more about seeing how very, very small things add up to cause behavior for very, very, very large things. Now, you also take a communication literacy course. This is basically like an English class where you like write essays, you read some stuff. A quick note on that. A lot of engineering students tend to kind of only value the technical classes, and they only think that, oh, I only want to learn the physics and the math, and I only want to learn the software, and I don't want to learn anything that's too crazy. And I think that's a big mistake. I think one of the most powerful things you can do to differentiate yourself from other engineering students and other tech people is to develop a very strong foundation in the arts and the humanities. And this is actually something I learned from Steve Jobs. I mean, I kind of did that on my own in high school and in college, but I saw someone like Steve Jobs instill that knowledge in Apple engineers, and that he was saying that the reason Apple succeeded as a company is Apple was very, very good at the interface of the science and the arts. And I agree. For example, something like an iPhone is designed to be used very, very well. And the designers and the engineers were working together very closely to make a product like that. So if you're someone who's studying engineering, definitely do not underestimate your like electives or liberal arts classes or your English or your kind of classes of that nature. If you do not know how to write effectively, if you do not know how to communicate, if you do not know how to get your ideas across, you're going to be a very mediocre engineer, because no one's going to even understand what your ideas are. So it doesn't matter how smart you are. So that pretty much covers the spring semester for computer engineering. As far as electrical engineering, you again take the Calc 2 and the Physics 1, which we just covered, but you start taking digital principles. This is a very important class where you start learning the language of computers. You start learning about binary numbers, right? And you start learning how to perform operations in binary. So for example, like, I don't know, binary addition operation. You start understanding how to break numbers that are like usually decimal. We humans like to use decimal because we have 10 fingers. So that's the convention that we started using. That's why we go like from 0 to 9. And in this case, computers like to use binary. And there's a reason for that, because computers are built on transistors and they're devices that switch on and off. But actually also like having like only two values that you can switch between, in this case a 1, a 0, or on and an off, also gives you the largest amount of robustness and the simplest foundation possible for doing mathematical operations. So it actually works out really well from a mathematics perspective, but also from an electronics hardware perspective. So just to give you the two reasons for that. So yeah, you learn how to do that. Now in computer engineering, you don't get into that class until spring of your sophomore year. So digital systems in this case is pretty much almost the exact same class as digital principles. You still learn about like how to do binary addition operations. You learn like things that are a little bit more intense, like logic gates, things that look like this, that basically perform the operations with the binary values. And then you learn how these things are built as well. Then you learn like a little bit more sophisticated digital circuits, which I'm going to get into in the later courses. But generally speaking, you learn the same stuff over here as well, which makes sense because in both electrical engineering and in computer engineering, you want to learn how computers work in general, and you want to learn how electronics and circuits work on a digital level. Now, one thing that's very important I want to backtrack is before you jump into your second year, between your first year and your second year, you ideally would have done some type of undergraduate research or like some type of project in the summer, or maybe even applied for some internships and gotten some. If you did not, that's okay. It's not the end of the world. A lot of people switch their majors, like in the United States, maybe around this time. So they use this time to basically take summer courses or things of that nature. But definitely try your best to do something during the summertime. Okay, so then in the fall semester of your sophomore year in electrical engineering, you take differential equations, which is basically a math of class that, again, builds up on this concept of the rate of change. But now instead of having one thing changing and you're tracking it, now you have two things or three things that are changing at different orders, at different rates entirely, and you're trying to see how they coexist in a system. This is basically what a differential equation looks like. And again, I'm not going to touch on this too much because I have other videos covering this. But basically, you have something over here that's, I don't know, like to the fourth order, and this is something that's not to that same fourth order. It's like a much lesser order, but they're existing in the same equation. They're basically two. It's basically a system with two variables that are behaving in completely different orders of magnitude. That's what dictates a differential equation. You learn how to first study these differential equations because they model behavior that is in the natural world, but then how to actually use them to build things, such as like machines and electronics and electronic circuits and things like that. You also take physics 2, which is electromagnetic physics. So in physics 1, you learn about mechanics, which is based on Newton's laws. In physics 2, you learn about electromagnetics, which is based on Maxwell's laws. So Maxwell's four equations. I don't know if you've seen these guys before. This is basically the foundation of all electromagnetic physics. It basically simplifies down to these four equations, where one tells you about the behavior of electric charges. The other one tells you there's no such thing as a magnetic charge. Then it tells you that the relationship between magnetic fields induced by an electric field. And then here it shows you that a magnetic field can be induced by a changing electric field or a changing electric current. If you understand these four concepts, that is literally like electrical engineering in a nutshell, right? Obviously, it gets a little more advanced than that, but on the fundamental physics level, those who understand those four equations can, in theory, understand everything else that's in here, because everything is built on top of that. Likewise, in physics 1, mechanics, if you understand the very basic principles of like how forces are operating in the macroscopic world, you can go like build anything. You can understand any material. You can understand how things are behaving, at least in the macroscopic world. Where things get a little funky is in the like very microscopic world, which is not only ruled by electromagnetics, but then on a much even smaller scale is ruled by quantum mechanics, which you learn a little bit about that in physics 3. This is basically waves, optics, and quantum mechanics. It's a very important class. But in computer engineering, you basically stop, I believe, at that point. Yeah, you kind of stop at physics 2. You don't go a little bit deeper. Which brings me to another important point. If you're deciding between electrical engineering and computer engineering, you have to understand that electrical engineering is a lot more physics oriented. Think of it as a spectrum where like you have electrical engineering on one end, and then you have computer science on the other end, and you have computer engineering in the middle. And on that same spectrum is like the amount of physics that is involved. In electrical engineering, you're studying the physics and you're getting a very deep understanding of it. In computer science, there's almost no physics, very rare. And even if there's like, I don't know, some universities will have you take a physics class, you don't really think about it in terms of physics. And then there's computer engineering, which is like kind of halfway in between, because you're doing like some hardware, some software. So if you're someone who hates physics, absolutely, I would definitely run away from electrical engineering. If you're someone who loves physics and is fascinated, especially by electromagnetic physics, like invisible things, then I would definitely run towards electrical engineering. I think I'm someone who loves physics. I love electromagnetic physics. I love electromagnetic waves, which is why I work on antennas mostly. So electrical engineering was a no-brainer for me, and I had to learn that through iteration, and I have other videos discussing that. So you take the follow-up math class, the physics class, and then you take circuit analysis, very important class. So circuit analysis, basically where you start learning about circuits, which is basically how electricity behaves in metals, usually in conductive material. In this case, you have some type of, well, it's an ammeter. We want something very, very simpler. In this case, you have a battery that's lighting a light bulb, and then you switch this thing on and off. It's a very, very basic. This is probably the most basic circuit. You do need like a resistor in there, unless in this case the light bulb is assumed to be the resistor, which is how like very old light bulbs used to be, but they are of course very inefficient, and like 95% of the energy would be heat and only 5% would be light. Now we have much more efficient light bulbs. So that's where you learn the basics of that, and you obviously learn a bit more advanced stuff like capacitors, inductors, little more interesting electronic components, and then you take a STEM communications major. I believe this is also like a technical writing class. On the other hand, for computer engineering, once you finish your physics 2, and you do take circuit analysis as well, you take systems programming and you take discrete structures. Now, discrete structures is like a very math-centric class. I would argue this is actually probably like the first like actual computer science class that you take. What I mean by that is in the intro to CS, what was happening in my university when I attended, these classes were kind of very application centric. Like you would start like programming right away. They were kind of software engineering classes. And even though you learn the very basics of like functions, variables, things of that nature, you're kind of coding, figuring out why your code breaks, debugging, getting into the habit of doing all that, starting to write more sophisticated code, whatnot. But discrete structures is the first time where you start actually learning about like kind of like the theory, the deeper theory behind computer science. Start learning about like combinatorics and the math branches involved with like how the data is organized and how the data flows, for example. You start learning about how to I don't know, like place your data in like trees and things like that. It's very mathematical and it's very, very theoretical. It can be a big nightmare. The follow up to it is data structures, which even though this is like probably one of the most difficult classes in the major, I would argue that this class is a little bit nicer because it's more practical, more applications oriented. Where like here you're learning purely kind of the math behind computer science. Here you start actually seeing how it works out in things like arrays, for example. And this class, I remember my friend would complain to me about it all the time because there's just so much to learn. There's a lot of concepts to learn. But I would argue that this class seemed to me a lot more visual and a lot more graspable. It just was basically a lot of work. The concepts were still very, very difficult. In my opinion, these two classes are, again, kind of a follow-up weed out classes where like in these two classes over here, the introduction to computer science, you're trying to see if someone can actually sit down and write piece of code and think critically, and if they can debug their code, not if they can ask for help. Here you're starting to understand if this person can actually genuinely understand computer science. And I'm not talking about software engineering. I'm not talking about programming or coding. I'm talking about like actual computer science, like the actual math and the algorithms and the patterns and the structure in which modern computing is built upon. So I think this is also a very, very important class or sets of classes. If you survive these two classes, then you are doing very, very well. Digital systems, like we mentioned, you start learning about binary. I think this is generally a pretty easy class. Calc 3 is basically Calc 1 / Calc 2, but in multivariables. So in this case, for Calc 1 and Calc 2, you're only really studying one variable. Like you're only looking at, for example, position X or time T, and you're trying to take that one variable and things are changing. In Calc 3, things become more spatial. You're dealing with like X, Y, Z. This goes hand in hand with electromagnetic physics because, for example, like an electric field is spreading spatially in 3 dimensions, and you want to be able to understand how the electric field is changing over time in space. For that, you need Calc 3. You cannot only do that with Calc 1 or Calc 2. You do the same over here in electrical engineering, and then you take differential equations, which you take in the fall in computer engineering. Physics 3, we talked about it. Physics of optics, waves, quantum mechanics. But then, and then there's a programming for engineering class. When I took it, that was in MATLAB. MATLAB was a very, very good programming language. A lot of CS people claim it's not a programming language. I think it is a programming language. And it's actually a very good introductory one. It's a very good, it's an application and it has a very nice graphical user interface. But I think that makes it even better, even easier, even nicer to use. There were years where this was taught in C++ or C, and I thought that was really, really stupid because in embedded systems you learn C and C++, and because you need C and C++ to program microcontrollers, and I thought it was much nicer to learn MATLAB in one class and then C, C++ in another. Like during your bachelor's in electrical engineering or in engineering in general, you want to learn as much as possible. Like you want to get as broad of an exposure as possible. And then once you do that as well, there's this class, signals and systems. This is probably my absolute favorite class in all of college, honestly. At least the technical one. You start learning about like what is a system, and the inputs and the outputs, and how a system defines the relationship between an input and an output. You also learn about the Fourier transform, which is a very, very important concept. Thanks to the Fourier transform, this microphone is able to pick up my voice, decode it, process it, make it sound really, really crisp, and deliver it to your ears. Thanks to this guy. Because what the Fourier transform basically does is it basically takes a time domain signal and converts it to a frequency domain signal. Now, once we take a signal in time and we're able to break it to its frequency components, we can then analyze it and manipulate it and do all sorts of cool mathematical operations with it. And then we can convert it back to time and then deliver it back to your ears so you can hear very, very crisp audio. So it's a very, very cool class. Obviously, it's not only relevant for audio, it's relevant for like any type of signal processing, like wave behavior. That's not what I wanted to do. So that pretty much covers the first 2 years for electrical engineering and computer engineering. I know I'm kind of jumping back and forth, but I kind of want to give you an idea of like how there's a lot of similarities, but yeah, there's a lot of differences. If you've made it this far, congratulations. You've pretty much got what it takes to be an engineer in either major. But this is also very important time. It's now summertime between your second year and your third year. Again, you should be applying for internships like as early as your fall sophomore year, maybe spring sophomore year. If you do not get an internship for the summer, that's okay. Try to do undergraduate research. If you're not part of a research institution, try to reach out to another one nearby. If you don't have one nearby, try to find a project or a club or an extracurricular activity to work on. The idea is you want to do something because like during the school semester, you're kind of really busy with classes. And yes, you can still work on projects, and I would strongly encourage you to do that and join clubs and join activities and things of that nature. In the summertime, you have the ability to work on something full time. So you're able to make a lot more progress during the summertime. Now, I remember my summer sophomore going into junior year, I stayed and I did undergraduate research in a space lab. And up until that point, my first 2 years, I was a lot more interested in medicine. I was a lot more interested in the human body. But thanks to that experience where I stayed in the summer and I worked on cool space stuff, it changed my career trajectory entirely because now I was like, hold on a second, this space stuff is really, really cool. And a few years later, I work at NASA, so it's like sometimes an opportunity in the summer or even staying at your school, finding a professor, doing some research with them can teach you things that you cannot really learn regularly throughout the school year. So that's very, very important. Okay. So now we get to third year, which is like arguably the most difficult year in terms of the content of the classes. However, I would argue sophomore year, freshman year is the most difficult psychologically because you're transitioning into college, and college is way harder than high school, especially if you went to a great school like UB in this case. And second year is very, very difficult because the classes start getting very, very difficult and you're not used to that level of difficulty. Third year, the classes are even more difficult or even more advanced and sophisticated, but you have kind of built the mental stamina and the work ethic from the first 2 years. So to me, third year was actually not bad. For me, the most challenging semesters in college were my freshman fall and my sophomore fall. Those were very, very, very stressful semesters. And yeah, so your third year in electrical engineering, you take electronic devices and circuits. It's basically a class where you start learning about little more advanced circuits, like more than just capacitors, inductors, resistors. You start learning about things like diodes, which are like devices that make electrical current go only in one direction. You start learning about transistors, which are the foundation of our modern technology, pretty much. Basically a 3-terminal device that can either act as a switch to turn things on and off in the digital world, or in the analog world, this can be served to amplify electric currents. So, and this is actually a really, really cool. So like, because it has 3 terminals, like you can think of like two like a connection. And then the third one is like deciding whether it should be on or off. That's the digital application. Or in the case of an amplifier, like you have, again, like one input, one output, And then you have a second input that's kind of feeding extra power or energy to that input. So it's like amplifying the current or the power or the strength of that input. So it's kind of a very cool way to visualize the fact that it has 3 terminals. This is what it would look like on a circuit diagram. This is one type of amplifier. There are different types, transistor. And then there's an intro to electronics lab, where you basically take these guys and put them on a breadboard, which looks like this breadboard. And you basically start plugging things in. Obviously, this is this is just a bunch of wires. Like, let's say breadboard. Again, same example, transistor amplifier. Yeah, so you see our friend, our 3 terminal friends over here. And then you obviously can look at the circuit diagram for that. In this case, this is a audio speaker. So you learn about that. You do take these 2 classes as well in computer engineering. So you have this 310 and then you have 312. This is very, very similar to 352. Now, again, because if you're going to learn computer engineering, you need to understand electronic circuits, because processors are electronic circuits. RAM is an electronic circuit. Any type of embedded system is an electronic circuit. So you need to have just as good of an understanding in electronics, in computer engineering, maybe even better than you do in electrical engineering, right? Because again, computers are basically electronics, versus with electrical engineering, you can go work on non-electronic things, such as like energy systems or things like that. So very, very important for both majors. You take applied electromagnetics, which is a follow-up of physics 2. Now in applied electromagnetics, not only do you learn about Maxwell's equations from an applicable perspective, you start learning about things like transmission lines, and you start learning about antennas, which is, I could talk all day about antennas. This is what I did half of my PhD on, or the second half of my PhD on. Antennas are very, very, very cool. They're basically devices that transmit, receive, reflect electromagnetic signals at various frequencies. So you learn that, and then you learn about probability and statistics. And I believe you learned that as well over here, although you do it in the spring. Probability and statistics is very, very important class. Not only from a technical perspective, like not only from the fact that you have to, for example, in signal processing or in antennas or in communication, like when you model noise, noise usually looks something like this. It's kind of like very, very random, very often, or at least modeled randomly. And in order to understand, like, or to predict behaviors like this, you need to understand probability theory, right? But what I found fascinating about this class is everything I learned here, like this class kind of traumatizes you in a very good way. And that ever since I took this class, I started thinking about like everything in probabilities. And I'll give you an example. Like a few days ago, I was doing something very unintelligent. Basically, I'm in East Texas right now. As part of my job, I'm traveling here temporarily to do some testing at a NASA facility nearby. And I was walking in the woods barefoot by myself, not very smart. And I something poked my foot, like a splinter or something went on, and it really, really hurt. And first 5 minutes, I was like, who cares, whatever. Like I just kind of tried to walk it off. And then after like 10 minutes, started hurting more. After 20 minutes, started hurting more. After 30 minutes, it was like extremely painful. I could barely walk. So I got in my car, and luckily it was my left foot, so I could still drive because I'm using my right foot to press on the pedal. And I drove to nearby urgent care. And the doctor looked at me and said, hey, if you want, there's a good chance something got in and it's stuck in there and it may cause an infection. You have 2 options. We can either cut it up and try to take it out, like with a scalpel, just kind of cut it up and see if we can take it out. And then the other option is you just kind of leave it there and hope that your body pushes it out after some period. And the very first thing I told him made him laugh, because I was like, okay, if you do cut it up, what is the % likelihood that you find it and you're able to remove it? And he laughed, because patients usually don't ask this kind of question. Patients are like, oh, what do you think we should do? But I was trying to understand the probability that he's able to find it and then make the decision myself. And that's something I learned to do in this class. And he looked at me and he laughed and he said, probably 5%. And then I said, okay. And then even if what is the downside? What are the consequences? What is the % likelihood that you may cause trauma or you may cause like injury to the foot as a result of cutting it by the scalpel? And he said, oh, that's like 100%. So then in my head, I was like, okay, there's 100% this thing is going to hurt and cause a lot more pain and probably a lot more damage. And there's only a 5% chance that we may actually do something meaningful out of this. So I ended up opting out for just taking some pain medication and kind of like just walking it off. And thankfully, a few days later, ended up being not that bad. So that was a good decision. So anyway, just to give you an idea how some of the classes that you learn in here are really, really cool, because you learn how to think in engineering and in math terms in the real world. And I think that's very, very powerful. I think that's why a lot of entrepreneurs who study physics or study engineering go on to be like very, very build great companies. People like Jeff Bezos or Jensen Huang or Elon Musk. They all studied like electrical engineering or physics or something like that. And I'm confident that they take that line of thinking and they apply it to business as well, which I think is pretty badass. And then here you learn engineering computations or linear algebra. Usually linear algebra, I believe you learn linear algebra here as well. Linear algebra is basically just like matrix math. Very, very important. This is what linear algebra looks like. It's basically doing mathematical operations, but in matrices. This is very, very important, especially if you're taking if you're using a programming language like MATLAB. MATLAB stands, I believe, for Matrix Laboratory. So everything is done in these matrices. And again, it's a very organized way of conducting mathematical operations. And there's rules for whether like you're multiplying the entire matrix by itself, or you're doing like a piecewise operation where each value inside each matrix is either multiplied or added or whatnot with the other. So it's a very, very neat basically branch of math that helps you, especially with things like modeling, simulation, but also understanding like behavior in the real world. So that pretty much covers what you're doing in the fall. On the other hand, for computer engineering, you start learning about computer organization and you start learning about real-time operating systems. Now, this real-time operating systems, very, very important class. This is very embedded systems centric. Embedded systems are basically like little computers that are application specific usually. For example, I don't know if you've ever seen like a microcontroller that looks like this. So for example, your computer is a general purpose computer. It's a massive processor. That's not really an embedded system. Embedded system is more something like this. There's an example. There's an Arduino, which performs like kind of very, very specific things, especially when you program it to perform very, very specific things. This is really, really cool for both electrical and computer engineering, because what you learn over here in real-time OS is basically very similar to what you learn here in embedded systems applications. To me, this is the interface of hardware and software. This is the first time where, especially as an electrical engineer, you start understanding how software can immediately and directly impact the behavior of hardware, right? And in Arduino or in any type of microcontroller, you can write a very simple piece of software that can make one of these LEDs blink. Or that, for example, you can connect it to some device like an alarm clock, and you make that alarm clock like go off at a certain time. I think that's really, really powerful, because that's when you start learning that, oh shit, like this code that I'm writing is actually compiling and it's going in the metal and in the hardware and it's doing something, and I'm able to visualize what is happening to it. I think that's very, very cool. That was kind of like probably the main benefit of this class, embedded systems, and that it really helped me see the hardware software connection. Very, very, very cool. And we covered these classes as well. I believe computer organization is a bit more. I actually don't really remember what this class was more about. Oh, this is where you build ALU. You learn more about ALUs. Okay, so this is where you like understand the fundamentals of not just how to like write a simple line of code, but for example, in digital systems, we talked about how you can build like do mathematical operations and logic gates. To take it one step further, you learn how to build something called an ALU. This is an arithmetic logic unit. And you touch upon that a little bit in this class, but here you dive into it a little bit deeper. And this is basically the foundation of processing. This is the foundation of computing, because an ALU is basically a device it's a digital circuit. It's made with these binary logic gates, and it's basically performing different operations, such as adding, such as subtracting, such as shifting the position of certain values. And this is very, very important, because again, at the end of the day, what does a processor really do? What does a computer really, really do? All it's doing is basically performing like very simple arithmetic operations and other operations. And that's basically what the ALU manages, something you learn in here. And that pretty much covers everything over here. There's this STEM communications, which is, again, basic like technical writing. We covered that as well. And then in the spring, we covered the applied probability. Microprocessors, you dive deeper into microprocessors. So basically, again, the follow-up to like where this is kind of telling you the fundamental understanding is where you actually start diving really deep into microprocessors and operating systems. Linear algebra, we covered that over here. However, on the electrical engineering spring semester, things you start diving into a lot more branches of electrical engineering, because here what we're seeing, the general trend over here is you're learning a bit of software, learning a little bit about computers, and you're basically kind of progressing in that direction. And the little hardware that you learn, which is basically electronics, only serves to help you understand how those digital circuits that you're building operate. And then that's pretty much it. Here you start diving more into, again, the physics and the analog world. For example, in communication systems, you learn about how communication systems operate. For example, examples of communication systems are like walkie-talkies or your cell phone. Or, for example, me talking right now to you, me talking to this microphone, which then takes the information, puts in your ear. That's a communication system. These are very analog signals that are being transmitted in the air, that are being transmitted in free space. Obviously, there are digital components to them as well, but you don't really dive deep into that unless you take the elective later. This is basically an analog introduction to digital systems. Analog meaning like interfacing with real world values. Digital means ones and zeros. So digital is like man-made, human-made. Analog is like nature-made, or like things existing as they are. And then you learn about fundamentals of energy systems. This again, how do you generate energy? How do you convert energy from one source to another, from one medium to another? But more importantly, how do you distribute and organize the distribution of energy? For example, like electric grids and things like that. Me personally, I think this stuff is not very interesting. I know a lot of my subscribers who are electrical engineering students love energy systems and love power systems. I know that this is probably the most common branch of electrical engineering, because like in every country, you need to have good power systems and energy systems. I was a lot more interested in the communication systems and the embedded systems, the technology. I just feel like there's a lot more innovation that can happen here. Yes, here there's like electrification and there's like solar panels and things of that nature, but I think the rate of change of how fast things are advancing here compared to what's going on here in communications or in electronics or embedded systems, I personally think this stuff is way cooler. Again, it's just me personally. Not take my advice blindly. And then that's pretty much it. So now by the end of your junior year, again, you've gotten very versatile as a student here. You've gotten really deep into computers, processors, things of that nature. Then finally, you get your senior year. And at least in my university, at UB, this is very filled with electives. You start diving deep into things that you find interesting. You can take a class on lasers. You can take a class on optics. You can take a class on waves. You can take a bunch of other classes on whatever you want. Here, you do learn HDL-based design using either VHDL or Verilog. This is basically very different from how we do like conventional programming, where you like write a piece of code in Python and it compiles and then it like runs on a computer. Here, you're actually kind of like hard coding. Like this is hardware scripting. Like you're literally like writing out the logic gates and things like that. And this is relevant for things like FPGAs, whatnot. Over here, you take this hardware-software integration, again, follow-up of microprocessors. You also take a ton of electives. But then I want to touch on this class, computer architecture. I actually took this class. I took it as an E elective. I don't know why I did that, because basically it was a very hard class, because I had not taken a lot of these processor-oriented classes. But this was a very cool class, and I'm so glad I took it because it basically taught me computer engineering. And something really magical happens in this class. Whenever you're talking about architectures, like whenever you're architecting things always assumes that you have a deep understanding of the science. What I mean by that is, before you, like in computer architecture, you learn about pipelining and you learn about like sequencing and like how to make decisions on how the information actually gets processed. And when does information get interrupted by another piece of information? When does an interrupt work? When does an interrupt not work? When does a process take place? When does a process not take place? These are a lot of like human decisions, not like science decisions. And this is where like it becomes more of an art. And I think that's the beauty of engineering, and especially when you're like working on things from an architecture perspective or from a system perspective, is once you get a very good understanding of where things are bounded and where things are where things break. Once you know what the limitations are, you start having a box, and then basically within that box, you have the artistic ability to make that box as efficient and as beautiful as possible. I think it's a very underrated thing with engineering that not many people talk about, because a lot of people perceive engineers as just people who just build things and solve problems, whatnot. But I would argue like engineers are more artists than they are scientists, because once you get a deep understanding of the science just kind of becomes the playground, and it becomes the foundation, or like the first floor. Everything that builds on top of that comes down to your decision making as a human, and your ability to like imagine something in your head and go out and make it in the real world. This is why I think it's very, very important that you pay attention to your humanities classes and liberal arts classes, because that's where you learn a lot of this artistic stuff. Like a lot of my antenna designs and a lot of things that I design and build, like they require a lot of artistic abilities. And I did not learn these in physics. I did not learn these in math. I learned those from like, I don't know, writing, filming, directing, a rock and roll history. It's a class I took. Um, like, uh, like a lot of classes that are arts related start becoming very, very important. So again, just kind of my kind of advice I would give every engineering student that you probably don't hear very often. Become very good as an engineer, obviously. Learn the physics, learn the math, build very strong foundations, learn how to solve problems. That's really what matters the most. But if you really want to like enjoy engineering and you want to design and create and build things rather than just kind of get told what to do and do what someone else wants you to do, which you may have to do at times, then you need to have a good artistic instinct, and you need to cultivate that artistic instinct with hanging out with people who are not engineers. And then finally, there's the UB capstone. In this case, is basically your senior project in which you do to graduate. But yeah, pretty much this is in a nutshell the difference between electrical engineering and computer engineering. I hope you found this interesting. If you want to dive deeper into this stuff and you want to meet other electrical engineers or other computer engineers who are in the trenches right now, I will put a link to my free community, which you can join us and come hang out and talk about electrical engineering, computer engineering, whatnot. Other than that, if this is the first time, welcome to my channel. Go ahead and watch some of my other videos, and I will see you in the next one. Peace, love.